An isolated ground is a grounding system designed to keep electrical equipment separate from the Earth's ground. This isolation is typically achieved using a transformer that incorporates a non-conductive barrier between its primary and secondary windings. The primary function of an isolated ground is to safeguard sensitive electrical equipment from voltage surges and electrical noise that might be present in the Earth's ground. This is accomplished through several mechanisms. Firstly, isolating the equipment from earth potential. The equipment is physically isolated from the ground via the transformer's barrier, which prevents current from flowing directly between the equipment and the earth. Secondly, minimizing ground currents. By isolating the equipment from the earth, ground currents are significantly reduced. This reduction helps prevent disturbances originating from external sources like lightning strikes or power line faults. Thirdly, reducing electromagnetic interference, or EMI. The isolated ground system prevents EMI from entering the equipment through the ground connection. This ensures the integrity of signals and reduces noise that can interfere with sensitive operations. Isolated grounds find applications in a variety of settings. One application is in medical facilities. They protect sensitive medical equipment such as monitors, defibrillators, and imaging systems from electrical interference. Another is in industrial settings. They protect sensitive equipment in manufacturing, automation, and data processing systems. A third application is in telecommunication systems. They isolate equipment from ground potential and reduce noise and crosstalk between lines. Isolated grounds are also used in power supplies to provide isolation between input and output circuits, protecting sensitive electronic components. There are several benefits of using isolated grounds. Firstly, improve signal quality and integrity. Secondly, reduce noise and EMI. Thirdly, increase safety by protecting equipment from voltage surges and ground loops. Fourthly, enhanced reliability by isolating sensitive equipment from external disturbances. When dealing with electrical systems and grounding, several important concepts and considerations come into play. Grounding is a critical safety measure in electrical systems, providing a low impedance path for fault currents to return to the source, thereby tripping circuit breakers or fuses and preventing electrical shock hazards. The National Electrical Code, or NEC, provides comprehensive guidelines and standards for proper grounding techniques. Article 250 of the NEC is dedicated to grounding and bonding, outlining requirements for grounding electrode systems, equipment grounding conductors, and bonding of metal parts. Grounding electrode systems typically consist of grounding electrodes such as ground rods, ground plates, or underground metal water pipes that are connected to the earth. The purpose of these electrodes is to provide a stable reference point for the electrical system and to dissipate fault currents into the earth. Equipment grounding conductors, or EGs, are used to connect the non-current carrying metal parts of electrical equipment to the grounding electrode system. These conductors provide a path for fault currents to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. Bonding is the process of connecting metal parts of an electrical system together to create an electrically conductive path. This helps to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Isolated grounding is a specialized grounding technique that is used in situations where sensitive electronic equipment is susceptible to noise and interference. In an isolated ground system, a separate grounding conductor is run from the equipment to the grounding electrode system, isolated from the normal equipment grounding conductor. This helps to prevent noise currents from flowing through the equipment grounding conductor and interfering with the operation of the equipment. The NEC permits the use of isolated grounding under certain conditions, as outlined in section 250.96. To implement an isolated ground effectively, one should consider a few crucial aspects. Firstly, ensure proper installation. The isolated ground conductor must be installed in accordance with the NEC and must be properly sized to handle the anticipated fault current. Secondly, minimize ground loops. Ground loops can occur when there are multiple ground paths between equipment, creating a potential for noise currents to flow. To minimize ground loops, use a single point grounding system and avoid creating multiple ground paths. Thirdly, Use appropriate grounding techniques for sensitive equipment. Sensitive electronic equipment may require special grounding techniques to minimize noise and interference. This may include using shielded cables, filters, and other noise reduction techniques. Understanding grounding concepts and techniques is essential for ensuring the safety and reliability of electrical systems. Following the guidelines and standards outlined in the NEC, along with proper installation and maintenance practices, can help to prevent electrical hazards and protect sensitive electronic equipment from noise and interference. The earth ground serves as a reference point, ideally at 0 volts, but in reality, it can carry noise and current. This is where the isolated ground comes in. It provides a dedicated, clean path to ground, minimizing interference. To understand it better, let's firstly consider a standard grounding system. In a typical system, all metallic parts of equipment are connected to a common ground. This includes the chassis, enclosures, and any non-current carrying metal parts. The purpose of this connection is to provide a low impedance path for fault current to return to the source, allowing the circuit breaker to trip and disconnect the power supply in the event of a fault. Secondly, think about the problem of noise. Electrical noise can be generated by various sources, such as electromagnetic interference from nearby equipment, radio frequency interference, and ground loops. This noise can be injected into the grounding system and can affect the performance of sensitive electronic equipment. Thirdly, examine the isolated ground solution. An isolated ground provides a dedicated grounding path for sensitive equipment, separate from the normal equipment grounding conductor. This isolated ground conductor is typically run directly back to the main grounding electrode system or to a dedicated grounding bus bar. Fourthly, understand how it works. The isolated ground conductor is insulated from the equipment enclosure, preventing any direct contact with the metal parts of the equipment. This isolation helps to prevent noise currents from flowing through the equipment and interfering with its operation. It's important to note that isolated grounds are not a substitute for proper grounding practices. All equipment must still be properly grounded in accordance with the National Electrical Code or other applicable standards. The isolated ground is simply an additional measure taken to reduce noise and improve the performance of sensitive equipment. The NEC provides guidelines for the use of isolated grounds in Section 250.96. It states that an isolated ground conductor must be insulated from the equipment enclosure and must be run separately from the normal equipment grounding conductor. The isolated ground conductor must also be identified by green or green with yellow stripe marking. In practice, isolated grounds are commonly used in applications where sensitive electronic equipment is present, such as in hospitals, laboratories, and recording studios. In these environments, even small amounts of noise can have a significant impact on the performance of equipment. For example, in a hospital operating room, an isolated ground may be used to ground sensitive medical equipment such as patient monitors and life support systems. This helps to ensure that the equipment is not affected by electrical noise, which could compromise patient safety. In a recording studio, an isolated ground may be used to ground audio equipment such as mixing consoles and microphones. This helps to reduce noise and hum, resulting in a cleaner and more professional sounding recording. While isolated grounds can be effective in reducing noise, they are not a perfect solution. They can also introduce new problems, such as ground loops. A ground loop occurs when there are multiple ground paths between pieces of equipment, creating a potential for current to flow between them. This current can create noise and interference. To prevent ground loops, it is important to use a single-point grounding system where all equipment is grounded to a single grounding point. This helps to ensure that there is only one path for current to flow to ground. In addition to using isolated grounds, there are other measures that can be taken to reduce noise in electrical systems. These include using shielded cables, installing filters, and using surge suppressors. Shielded cables have a layer of conductive material that surrounds the conductors, which helps to block out electromagnetic interference. Filters can be used to remove specific frequencies of noise from the power supply. Surge suppressors can protect equipment from voltage spikes and surges, which can also cause noise. Isolated grounds are a valuable tool for reducing noise in electrical systems. However, they should be used in conjunction with other noise reduction techniques and should be installed and maintained properly to prevent problems such as ground loops. Isolated grounds are often used in conjunction with other noise reduction techniques. Firstly, filtering is employed to remove unwanted frequencies from the power supply lines. Secondly, shielding is used to protect sensitive equipment from electromagnetic interference. Thirdly, surge suppression protects equipment from voltage spikes and surges. The NEC guidelines are crucial for proper implementation. Section 250.96 specifically addresses isolated grounding, outlining requirements for conductor insulation, separation from regular equipment grounding conductors, and proper identification. It is important to note that while isolated grounds offer significant benefits, they are not a universal solution for all grounding problems. A comprehensive understanding of grounding principles and careful consideration of the specific application are necessary to determine the most effective grounding strategy. In addition to the NEC, other relevant standards and guidelines may apply depending on the specific application. For example, in healthcare facilities, the National Fire Protection Association, or NFPA, 99 Healthcare Facilities Code provides additional requirements for electrical safety and grounding. Similarly, in industrial settings, standards such as those published by the Institute of Electrical and Electronics Engineers, or IEE, may provide guidance on grounding practices for specific types of equipment or systems. The effectiveness of an isolated ground system depends on several factors, including the quality of the installation, the characteristics of the electrical system, and the nature of the noise being suppressed. In some cases, an isolated ground may not provide a significant improvement in noise performance, while in other cases it may be essential for ensuring reliable operation of sensitive equipment. When troubleshooting grounding problems, it is important to use appropriate test equipment and techniques to identify the source of the noise and to verify the effectiveness of the grounding system. This may involve using a ground resistance meter to measure the resistance of the grounding electrode system, or using an oscilloscope to observe noise waveforms on the grounding conductors. Proper grounding is an essential aspect of electrical safety and equipment protection. Understanding the principles of isolated grounding and following relevant standards and guidelines can help to ensure the safe and reliable operation of electrical systems in a variety of applications. By implementing isolated grounds, you can safeguard equipment, improve signal quality, and enhance overall system performance. Consider these points for better use. Firstly, assess the need. Determine if sensitive equipment requires an isolated ground due to noise issues. Secondly, plan the installation. Design the isolated ground system according to NEC guidelines, ensuring proper conductor sizing and installation. Thirdly, implement correctly. Install the isolated ground conductor separately from the regular equipment grounding conductor. Fourthly, verify performance. Test the system to confirm noise reduction and proper grounding.